Hello and welcome to our second lecture covering Lesson 2-5, Why Can't We Travel in Space Easily? As you look at these lectures, please provide me with feedback. If they're working well for you, I'd like to know that. If they're not, I'd like to know that as well. And if you have suggestions for how I might do them differently or change them up, that would be very useful for me to know. I know in the first one I think the audio was a little low, and I'm trying to play with that a little bit and see if I can't improve that here in this second video. Feel free to email me with your comments or feedback or use the discussion forum that I've created within Moodle. On page 141, we begin to talk about why can't we travel in space easily. And this section starts off with some cooperative group problems that we're going to go through together. We're initially told that the minimum distance from Earth to Mars is approximately 35 million miles, and the minimum distance from Earth to the Moon is 225,600 miles. And we're asked to create a ratio of the distance from Earth to Mars and the distance from Earth to the Moon. So we'll assume that we're creating a unit ratio. On the left, I've put the distance to from Earth to Mars, in the top, since that comes before the word to and after the word ratio, and then the distance from Earth to the Moon in the bottom. That comes after the word TO2, equal to x over 1. And if we do that math, we find out that there's about 155 miles to Mars for each and every mile that there is to the Moon. So in question 2, when it asks how much farther is Mars from Earth than the Moon is from Earth, we can simply say that Mars is 155 times farther away. So it should take about 155 times longer to get there. On the next page, we're told that the Apollo spacecraft took about 3.16 days to get to the Moon. And we're asked if we traveled at about that same speed or rate, how long would it take us to get to Mars? Well, what we can do is create ratios that compare the number of days and the number of miles. So on the left here I've put 3.16 days for the time it takes to travel to the Moon. On the bottom I have 225,600 miles, that's the distance from the Earth to the Moon. On the right, we don't know the number of days it would take to travel to Mars, but we do know the distance of 35 million miles. So I put days on the top on both sides, and I put miles on the bottom on both sides. If we solve our proportion, we get about 490 days, which is a lot of days, and not necessarily the best way to talk about that time. So I went an additional step, and I converted that number of days to years. And if we take what we know to be true, 1 year is composed of 365 days on the left, and we compare that to an unknown number of years to the 490 days on the right and solve that proportion, it comes out to about 1.3 something years, or about 1 1/3 years. You could think of that as 1 year and 4 months. In other words, it takes an awful lot longer to get to Mars at the same speed we went to the Moon than it did to get to the Moon itself. And keep in mind that once you get there, you probably want to do some stuff and then you want to turn around and come back. So you might be looking at like a 3-year trip. Not an easy thing to do. In our next bit of material, we're going to introduce 3 formulas, and they're really the same formula, just written in a variety of different ways. And these are things that you guys actually all understand pretty well just on your own. If you look at, oops, let me delete that for a second here. If you look at this sentence, the second sentence here, for instance, if you walk at an average speed of 3 miles per hour for 2 hours, you travel a total distance of 6 miles, 3 miles per hour times 2 hours. You guys know this. If you travel in your car at 50 miles an hour for 2 hours, you're going to go a total of 100 miles, 2 times 50. If we arrange that formula a little bit, that formula is distance is equal to rate. When you see rate, think speed. So distance is equal to speed times time. If we rearrange that a little bit, we can say that the speed is equal to the distance divided by the time. If we travel 200 miles and we do that in 4 hours, 200 divided by 4 would be 50 miles per hour. That's all that formula is saying. And finally, if we rearrange one more time, we can write the formula time is equal to distance divided by speed. And that's something you guys are also fairly familiar with, I'm guessing. If we traveled 200 miles and we did that at 100 miles an hour, It should take us 2 hours to do so, so we can figure out the time from that. You'll want to refer back to these formulas once in a while as you work through the material in this lesson. I'm going to give you a few hints for the cooperative group problems. I'm not actually going to work through them. So you may need to pause this video at some point to write some of these hints down, and please feel free to do so. For number 1, remember that the distance from Earth to the Mars is 35 million miles. To actually determine how fast you would have to travel to get to Mars to answer this question, you need to convert the 2 weeks to hours, and you can do that using the facts that there are 7 days in 1 week and 24 hours in 1 day, so that'll be a 2-step process to convert that. Once you have miles and a time in hours, you can use the rate is equal to distance divided by time, or speed is equal to distance divided by time formula to get your speed, and that'll be in miles per hour. Question number 2 says if we flew from New York to Los Angeles at that same speed that you've just calculated, how fast would you get there? So here we're looking for a time. So your distance is going to be 2,450 miles. Your speed is going to be the speed you just found in the previous question. And your formula is going to be the fact that time is equal to distance divided by speed. Your answer is going to be a pretty small number in terms of hours, so you should convert that answer from hours to minutes so it makes a little more sense, and you can do that using the fact that 60 minutes is equal to 1 hour. Question 3 just asks you how far is Neptune from the Earth. It's 2.68 billion miles, so you'll want to make note of that. In your last question, the top of page 144, you're asked that if you traveled the same rate as the Apollo 11 spacecraft, how long would it take to get to Neptune? So you're going to want to go back to page 142 and look at the problem that we did at the top of that page. And you're going to use that same strategy, but your distance is going to be the distance to Neptune instead of the distance to Mars. For the next little bit of instructor-led problems, I'm going to shift over to a different copy of the book. We're first asked to look up how much distance a light year represents. It's kind of weird that we call it a light year and it's a measure of distance, but it's the amount of distance that light travels in 1 year, and that's 5.88 trillion miles. We can write it without the word trillion this way. If you travel that distance in 1 year, how fast would you actually be going? Well, there are 365 days in 1 year, and that's some number of hours that we'll need to figure out. We can use the fact that 1 day is comprised of 24 hours to solve, and we'll find out that in 1 year there are 8,760 hours. We need our time in hours so that we can work with miles and hours to get a speed in miles per hour. We'll use the speed formula. Speed is equal to distance divided by time. Our distance is at 5.88 trillion miles. Our time we now know in hours is 8,760, and when we divide to solve that, we'll find out that it's about 671 million miles per hour. In other words, light travels incredibly fast. Question number 2 says that we see talks about seeing spacecraft in science fiction films that travel at light speed and even faster. Think about what would happen if you hit a small rock at that speed. Think about what it feels like to get a little bit of a spray of sand or something on you, like if the wind blows sand on you, what that can feel like. And those are really low speeds compared to the speed of light. So imagine that sand coming at you in faster and faster and faster speeds, eventually up to about 671 million miles per hour. What do you think would happen? For part B, we're asked to compare how fast we would hit the rock to how fast a bullet travels. All right, so I did a little research and I found that muzzle loaders, which are pretty slow guns, their bullets travel about 390 feet per second. For high-powered rifles, it works out to about 3,900 feet per second. I chose to work with the 3,900 feet per second. And the first thing that I did was convert 3,900 feet per second to miles per hour. And I did that in 2 steps. I took the 3,900 feet and converted that to miles first, using the fact that there are 5,280 feet in 1 mile. And from that I found out that 3,900 feet is about 0.739 miles. And then I took the 1 second that's in the bottom. Remember, what we have in the bottom of these units is really just one of whatever the unit is. So I converted that 1 second to hours. And I used a lot of decimal places so I'd have enough numbers to work with. And I ended up with 0.000278 hours. Then I used the speed formula. I took the 0.739 miles that I've just found, and I put the 0.000278 hours number that I found, and I found out that 3,900 feet per second is approximately 2,658 miles per hour. It's a lot slower than 671 million miles per hour. And if we divide the 671 million miles per hour by the 2,658 million, or excuse me, 2,658 miles per hour, that is essentially create a unit ratio, we'll find out that the speed of light is still about 250,000 times faster than a bullet from a high-powered rifle. From there, you've got some at-home practice problems. Answers are in the back of the book to practice with. The cooperative group problems that you have, you can work on those and answer in Moodle, and Moodle will tell you if you're right or you're wrong. As always, if you get stuck on anything, please ask during our Zoom meetings or send me an email or post to the discussion forum. I am here to help. Just because we've moved to a distance learning format does not mean that you are in this alone. I am still here to help and will do as much as I possibly can.